Hello, welcome to the lecture course CHO 351. In previous lecture, we have discussed about the off resonance decoupling 13 C NMR spectra. Also, we have discussed about the depth technique in 13 C NMR spectroscopy. So, in this lecture, we are going to discuss about the problem based on 13 C NMR spectroscopy. Problem based on 13 C NMR spectroscopy. So, before that, you must know the approximate 13 C chemical shift value for selected type of carbons. Approximate 13 C chemical shift ranges in ppm for selected type of carbon. So, R methyl 8 to 13 ppm, in this range we can observe this carbon. Then R2 CH2 15 to 55 ppm, in this range we can observe this chemical shift. Then R3 CH, then 10 to 16 ppm, in this range we can observe the chemical shift value. Then attachment to iodine 0 to 14 ppm, in this range we can observe the chemical shift value. Then carbon bromine, means bromine attachment 25 to 65 ppm. Then attachment to nitrogen 30 to 65. Carbon chlorine 35 to 80. Carbon to oxygen, that is the 40 to 80. Then alkyne carbon 65 to 90 ppm. Then alkene carbons 100 to 150 ppm, in this range we can observe. Then cyanide carbon 110 to 140 ppm. Then 110 to 175, in this range. Then ester, means carbonic carbon in ester. Then in acid, then in amide. So in ester, in acid, in amides 155 to 185, in this range we can observe the carbonic carbon. Then carbonic carbon of either aldehydes or either ketone 185 to 220 ppm. Okay. So this is the approximate 13 C chemical shift value for selected type of protons in ppm. So, alkyl group attached to another alkyl group, that time we can observe the chemical shift value from 8 to 16 ppm, in this range. Okay. After that, carbon is attached to electronegative element like iodine, bromine, chlorine, nitrogen and oxygen. That time, that is the hydrogen less electronegative. So 0 to 40 ppm in this range we can observe the chemical Stru value. As compared to bromine, as compared to iodine, bromine is electronegative. So 25 to 65 ppm in this range we can observe the chemical Stru value. Then nitrogen is more electronegative than bromine, then 30 to 65. Chlorine is more electronegative than nitrogen, then 35 to 80. Oxygen is one of the most electronegative element in the periodic table, so 40 to 80 ppm. So this we can observe for carbons. Then alkyne carbons 65 to 90 ppm. Then alkene carbon, so because of hybridization and diamagnetic anisotropy effect, 100 to 150 ppm. Also nitrile carbon because of diamagnetic anisotropy effect, also because of nitrogen attachment, 110 to 140 ppm. Then also aromatic carbons 110 to 175 ppm you can observe. Then carbon in ester acid amides, also in aldehydes and ketone, 155 to 220 ppm. So you know the range, that is the 0 to 220 ppm. This is the 13C chemical shift range. So in exam there are 3 types of problem that may be asked. So there are 3 types of problem that may be asked in exam based on 13 C NMR spectroscopy. So types of problems that may be asked in exam. That is, the first is the assign the chemical shift value. Assign the chemical shift. Assign the chemical shift to various carbon present in following compound. Present in the following compounds. In following compounds. So in this type of problem, the chemical shift value means chemical shift value is provided to us, and also structure is given. Over the structure you have to assign the chemical shift value to carbon. So this is the first type of problem is asked here. Then second type of problem is to reduce the structure from given CMR data. So here in this kind of problem of resonance decoupling 13 C NMR spectra, that information provided here. Also sometimes depth information means DEPT. Last time we have discussed depth technique. That information is also provided. So from this information you have to do the structure. So this is the second kind of problem, and third is the deduce the structure from given CMR and 1H NMR data. Okay. So this is the third type of problem that may be asked here. That is you have to do the structure from CMR as well as 1H NMR data. Sometimes simple of resonance decoupling 13 C NMR information is provided. Sometimes depth information is provided along with 1H NMR data. So here in this lecture we are going to discuss first type of problem here, that is the assign the chemical shift value to various carbon present in the following compound. So this type of problem we are going to discuss here. So in this lecture we will discuss two examples. So first example we consider here, that is the first type of problem we are going to discuss here. So assign the 13C, chemical shift to various carbon in following compound. In the following compound. So this compound is given and 13C chemical strata is given. 24T means triplet signal, then 6.112 means triplet. Again, this is a chemical strata along with its signal here. Of resonance decoupling 13C NMR spectra. 120.26 triplet, then 120.82 singlet, 129.44 doublet, 130.72 singlet, 144.66 singlet, 150.88 doublet, 150.20 doublet, and 163.46 singlet. So here triplet, singlet, doublet, singlet. So this information is nothing but number of attached proton over the carbon. Means here we have to consider the one bond coupling between carbon 30 and 1H nuclei. So this information is nothing but of resonance decoupling 13C NMR spectra. So over this structure we have to assign the 13C chemical shift value to various carbon present in the compounds. So here firstly we again rewrite this compound. So after rewrite this compound, we write here the signal given by each carbon. So this carbon bear the one proton, one hydrogen. So this is the doublet. Okay. This also bear the one hydrogen. So two doublet. So this not bear any proton. So this is the singlet. So this also is the singlet. This also is the singlet. This also is the singlet. So this gives the triplet. This gives the triplet. Okay. This have the one hydrogen. So gives the doublet, and this gives the triplet. So this signal is given by the carbon by considering the one bond coupling in off resonance decoupling 13C NMR spectra. So here firstly we are going to assign here simple signal. So here 163.46. This is one of the downfield value, and this downfield value, largest downfield value because of carbonyl group. So this carbonyl group shows the signal that is singlet. So for this carbonyl group we can assign the value 163.46 singlet. Okay. So for the carbonyl group, you know that carbonyl group is appear in the range that is the 155 to 220 ppm. In this range we can observe the carbonyl carbons. So here anhydride, cyclic anhydride. So for this we can observe the 163.46 singlet. Okay. So we have assigned this signal. Then 150.20 doublet, 144.66, also 150.88, then 120.44, also 130.72. So all these signals must be because of, means above the 100 here. Above the 100 means from this signal to this signal up to 150. So this signal must be come from aromatic carbons or either from alkene carbons. So you know the range, that is the 110 to 150 ppm. So here 1, 2, 3, 4, 5. Okay, and these 2, 6, 7. Okay, 1, 2, 3, 4, 5, 6, 7. So 7 aromatic or either alkene carbon is present, and also 7 signal is given that have the chemical value above the 110 ppm. So we have to assign this value here. So here singlet signal, that is the 144.66 ppm, that is the singlet. So here this signal must be because of this carbon, that is the 144.56 singlet. And also again second singlet, that is the 130.72. So because of carbonyl attachment 130.72, for this carbon we can observe the singlet signal. So for these two carbon we can assign these two values. Okay. So 144.66 and 130.72, these two signals we have assigned here. Next is the 150.20 and 150.88. So because of nitrogen attachment, so for this we can assign the value 150.88 and doublet. Okay. For this we can assign the 150.20, that is the doublet. So for this we can assign the value. So because of nitrogen attachment and also because of carbon attachment, for this we can observe the downfield value 150.88. Also because of nitrogen attachment, for this we can observe the 150.20 ppm. Okay. So also one singlet 120.82 singlet. So this, for this carbon we can assign the 120.82 singlet. So for this carbon we can assign the 120.82, that is the singlet signal. So here to this carbon we can assign the value 144.66 singlet. For this we can assign the 130.72 singlet. Okay. But to this carbon 120.82 singlet. So because of this double bond is conjugation with this double bond. So because of this carbon is shielded here. When you write the resonance structure, in that resonance structure you can observe that this double bond come at this position here. And because of that, this carbon is a shielded carbon. So because of that, we can observe the 120.82 singlet value. Okay. So we assign this value also. And remaining signal is that is the 120 triplet. Nothing but because of this carbon, this is attached to proton 120.26 triplet because of attachment to two protons or hydrogens, and to this carbon we can assign the value that is the 129.44, that is the doublet, because this is attached to single proton or hydrogen. And remaining two signals, that is the 24 triplet and 66.12 triplet. So here this shows the 66.12 triplet, while this shows the 24 triplet, like this. 24 triplet. So here because of oxygen attachment 66.12 triplet, and this shows the triplet 24 triplet. Okay. In this way we can assign the chemical shift value to various carbon in the compounds. Okay. So this is the problem number 1. In this way we can solve the problem, that is the assign the 36 chemical shift value to various carbons. So we also discuss here problem number 2, that is the same question, that is the assign the chemical shift value to various carbons present in the following compounds. So here firstly I write the signal here, then 174 point singlet, 98 singlet, then 74.5 singlet, doublet, 56.3 quartet, 52.4 quartet, 51.5 doublet, 39.1 triplet, 34.2 doublet, 31.7 triplet, 26.5 triplet, 24.4 triplet, 21.2 triplet, and 50.5 quartet. Okay. So this signal is given. We have to assign this signal over this structure. So structure is also given. So this structure is given. For this structure we have to assign this value. So before that, same like last problem, we have to First assign the signal triplet, 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 triplet and triplet. Okay. Then singlet, singlet, then doublet. Then here also the doublet, quadlet, quadret, quadret. Okay. Then this also shows the singlet, this carbon shows triplet, doublet, and this is again triplet. So in this way, this carbon shows the signal here according to off-resonance decoupling 13 C NMR spectrum. So firstly, we assign the signal to carbon and carbon. So 155 and 170. So this is the largest downfield signal here. So 150. So we can observe the 150 signal for this carbon and carbon. That's the signal singlet. 150. That is the singlet signal. And to this carbon, we can assign the signal as 170.4 singlet. So because of amide, and because of amide, what happened? Nitrogen lone pair is delocalized. So this carbon carbon is shielded. So 170.4, because that we can assign this value to this carbon. Okay. So next is the methyl carbon. This carbon shows the signal 50.5 quadrat. Okay. Then this carbon, remaining two carbon, that is the quadrat signal is given here. That is the 56.3 quadrat and 52.4 quadrat. So for this methoxy group, we can assign the value. For this methoxy group, we can assign the value, that is the 56.3 quadrat. Because this methoxy group attached to carbon, which is the secondary carbon, while this is attached to primary carbon. So this is value, that is the 52.4 quadrat. So this is more shielded, more deshielded as compared to this carbon, because of this is the attached to primary carbon. Next is the means we have assigned these two signals here. Overall, we have assigned the 1, 2, 3, 4, 5 signal. Then next is the this triplet signal. Because of nitrogen attachment, we can observe the signal for this, that is the 31.7 triplet. How much? 31.7 triplet. Okay, this triplet. Also oxygen attachment, we can observe the signal triplet as a 39 for this 39.1 triplet. Because of oxygen, the more electronegative, we can observe this signal 39.1 triplet. Okay. So next is the or this 24.4 triplet, and for this we can observe the value, that is the 21.2 triplet. So here, because of symmetric structure, this carbon give the same signal, also these two carbon give the same signal. Okay. So 31.7 triplet, both carbons show the same signal, also 24.4 triplet, both carbons show the same signal here. So in this way, we can assign these signals here, that is the 24.4, then 21.2 triplet. Then next is the 26.5. So this signal, because of this carbon, 26.5 triplet. Okay. So this carbon shows these signals. Then because of oxygen attachment, this carbon shows signal 51.5 doublet, almost 51.5 doublet, while this carbon is attached to also oxygen, so 98 Cl. Oxygen attachment, so 98 Cl. Also oxygen attachment 51.5 doublet. In this way we can assign the signal here. Also this carbon 74.5, that is the doublet. So because of direct attachment to oxygen, 74.5 doublet. So in this way we can assign the signals here. Also remaining signal is that this carbon 34.2 doublet. Okay. So in this way we can assign the 13C chemical shift value over these compounds. So in this way we can solve the problem that is based on 13C NMR spectroscopy. So in next lecture we will continue our discussion with problem based on 13C NMR spectroscopy.